Hello and welcome to our next lightning talk. I'm pleased to introduce you to Moritz Joseph, the co-founder and CEO of Roofline AI, an AI compiler startup. He is talking to us today about making use of level 0 with an end-to-end MLIR compiler. So if you have questions during his session, we're not going to be looking after them at the end, but we will be looking at questions throughout the session and we can answer them in text in the Q&A widget. So if you do have questions, just ask them in the widget and we will write in the answers during the session and afterwards. With that, I'd like to hand over to Moritz.
Eleanor, thank you for the kind introduction and welcome to my presentation today. I'm happy that you all joined and going to discuss today on our mission to also bring level 0 into our AI compiler toolchain. At Roofline, we are dedicated towards building an AI deployment solution that makes edge AI more simple, and as that, APIs that allow us to interface to hardware more easily are one of the core assets that we have to address. And therefore, we are excited to also getting in touch with UXL Foundation and showing how we are integrating one example API to our end-to-end compiler. So the problem that we are solving at Roofline in general is motivated from the relatively painful process of deploying AI models at the edge. And the reason for that is basically twofold. On the one hand side, we are in an environment where we have a lot of fast-moving algorithms on the AI side with ever new features coming to the market, and then somewhat slowly moving deployment solutions. So one example is TensorFlow Lite, which is quite old nowadays and still prevalent and cannot cover all the features that you need for modern LLMs. And then on the other hand, ever new chips come to the market. Platforms are getting more and more heterogeneous with diverse set of different accelerators, GPUs and CPUs within a single SoC, which calls for the need for a unified deployment solution. And that's what we are precisely trying to address. And this is all in a technologically challenging market in edge AI, where resource constraints are really critical and you have to meet the highest performance possible as well as low memory footprint. So all of our optimization tools are always tailored towards reducing the latency of the model execution as well as the memory footprint. So how do we do this? And for this, let's first take a look at our end-to-end tool flow here. So essentially our software development kit that we are developing is in between the end user's AI model as well as the chip that they are deploying to. And the key features of our software development kit are flexibility, efficiency, and then simplicity in terms of the ease of use. And what happens is that you can load your AI model, which is fully trained and quantized, into our SDK. And then we have a retargetable AI compiler technology within this SDK that allows you to address the target chip that you're looking for. And level 0 would be one example how to address the chip. And I'm going to explain in this talk more how we're doing this. So we are flexible both on the model side as well as on the chip side with this retargetability. And we are efficient in terms of the model execution speed as well as the memory footprint that we have. And everything that we provide is integrated into Python libraries that you can use from PyTorch, just as you are also using the PyTorch backend torch inductor or any other backend that you would find in the market currently. So to be more precise, what do we support on the model side and on the chip side currently? So as you can see, we are still a new startup. We have started at the beginning of this year, so we're not fully there with all chips and all models, but we have a full support for PyTorch, TensorFlow, ONNX and JAX models, and we basically can support all relevant models from Hugging Face I'm going to show in a second. So we're really focusing on this coverage that you can easily just run your target model that you want to run on your hardware. And then on the hardware side, we are constantly improving, and this is also part of this talk today, how we are adding more features and more platforms to our more devices to our software development kit. But within our ATIC backend, we are currently supporting any CPU, ARM, x86 or RISC-V. We are also supporting the relevant GPUs from AMD and NVIDIA, as well as via the SPIR-V interfaces, a lot of embedded CPUs that are available there. And then together with our customers, we're also bringing in dedicated NPUs or AI accelerators into our system so that you can also use them. They might be a little bit more on the DSP style side of things, but also on fully programmable AI accelerators, very similar to a GPU. So we are in general support. And as I already said, one of the core relevant features for us is this flexibility in terms of the models, and so that we are really enabling to bring all the new models onto these target chips. And for this, we are focusing on model coverage a lot. And I just want to compare our solution towards Torch Inductor today here with the top 10 Hugging Face models, just as a showcase on what we can achieve in terms of model coverage. So just a little bit of background for those not super familiar with how PyTorch works. So you have this Torch Inductor backend, which allows you to execute your AI model. And then if you are focusing on what is used on Hugging Face, you can just download the model, run it through your PyTorch toolchain. And then if you just run the inference, then it will run this Torch Inductor in background. And so basically our view on this is any model that runs through Torch Inductor, that's a model that we need to support as well, because that's the industry standard in terms of model support. And what you can see here for the top 10 Hugging Face models is that we are actually supporting all those models that are also without any further bug fixes or any code changes are running out of the box in PyTorch. So we are really proud about this. And the two models that we couldn't support, they are also not running in PyTorch. So that's more a model issue than an actual backend issue. And then also we have day 0 support for models. So this is showcased here by the new Llama 3.2 version. Where on day of release of this new model, we could directly run it with our toolchain. It was just working. So we're really proud about the coverage that we achieve. But obviously coverage is not everything. You also want to have good performance. And that's something that we are mainly focusing on after we achieve coverage to improve the performance. And so here, as I said, we are mainly going for the edge market. So our core two KPIs that we are focusing on are model latency as well as the memory footprint that you need, because if you have a slower memory footprint during execution, you can bring a more complex model onto your device or buy a smaller device, which is a financial advantage. And latency obviously is just good for edge AI deployments in general. And so here we have the same 10 models or 8 models actually that are running from Hugging Face in our toolchain and compare them against Torch Inductor. And what you can see, except for one model, we are outperforming the state-of-the-art execution pipeline significantly in both dimensions. So from like up to 3.5 to 4x in terms of latency improvement and up to 35x in terms of memory footprint, which obviously is a very advantageous result for us. But in general, we are also improving the memory footprint. And you always have to think about it as like an optimization between how much parallelization can you achieve in the model where you have a higher peak performance, so the latency is better, versus the memory footprint, because if you parallelize more, you need more live memory. So that's the key two things that we are optimizing for. And then also in the edge space, really relevant are still TensorFlow Lite and other solutions, and here we are also comparing against them, and you can see that we are here also giving a performance advantage. So for us, it's really about these two aspects, and we are achieving this with our end-to-end flow that we have implemented in MLIR, where you can read in any AI model into our front end. Then we do graph level optimizations, we do scheduling optimizations, we place the specific kernels then on the target hardware, and then you basically get two pieces of component here. And the one is the host code. So this is basically our runtime code that runs within the CPU in the system as a controller. And then you have different kernels for different devices. So you can have a CPU kernel that just runs on another CPU or a cluster of multi-cores. You can have a GPU kernel or even an NPU kernel. So you always in our toolchain have this runtime and the individual kernels. And this is also how we are integrating level 0 here, because we are basically integrating it within the runtime and then building kernel support on top of that through our kernel compilation toolchain for the specific target device, like an Intel GPU, for instance. And yeah, with this approach, we are able to do this end-to-end flow and going through the different levels of abstraction to meet the target hardware that we are looking for. And just to give you a little bit more insight on what we are doing for the kernel generation, so here are two exemplary tool chains. They are a little bit simplified, but the steps are well, generalizable in some regards. So we are really going hierarchically both the CPU and the GPU toolchain to tile the workload so that it fits the memory hierarchy of the target system, then to bufferization so that we can actually execute the model with the correct memory addresses, and then use the backend either via LLVM for the CPU or the ROCm or QVM for GPUs to generate the actual kernels. So this allows us to generate individual pieces of kernels, and then we need to run them on the target hardware, right? And for this, we have the runtime, and the runtime basically is a piece of C code that allows you to get the data in and out of the kernels, do all the memory management there, and invoke the kernel execution. And so what we are using there is basically an HAL, so a hardware abstraction layer. And within this HAL, what we are doing is that that we are interfacing towards the target hardware via a very simple C-style interface where you can run the kernel and then write data in and out of that. And this interface allows us, the HAL allows us to interface with the CPU, but also with different kinds of GPUs like via Vulkan or CUDA or Metal directly. And it's a super small runtime. It's really made for asynchronous execution, so you can invoke the kernel and then get it back. And everything's abstracted with this hardware abstraction layer. And basically, it's modeled after Vulkan without all the shader components. And then we also, in general, allow to direct bytecode modules or native modules if that's required, but not so relevant in terms of the level 0 support. And with this flexible runtime, we can now address different target hardware. And one target hardware that we are working, for instance, on is the GPU of the Raspberry Pi 5. It's a SPIR-V interface, so that's basically the development that we did before going towards level 0 here. And this allows us to run AI workloads on the GPU of the Raspberry Pi, basically doubling the performance of this platform, because before you could only run it on CPUs, and now we get around another 30 gigaflops out of the GPU to execute our AI model. And that's quite substantial if you think about it. And so, as you can see, this flexible runtime allows you to really integrate new devices easily. And if you have good interfaces like SPIR-V, you can directly run that. And this is why we're super happy about also something like level 0, because level 0 basically directly integrates with this hardware abstraction layer. And that is something you can see on the slide now, how this integration is done. So on the left-hand side, you have the level 0 API, how it's done, how it can integrate different scalar vector metrics or spatial units, and mainly it's currently working on the GPUs, right? And so basically level 0 gives you this direct to Metal API to offload your programs to the accelerator, and it's super close to the Vulkan Compute API. But it's not limited to GPUs. So the ergonomics are very nice for us because it perfectly fits the design of this hardware abstraction layer, and we could directly run it through the pipeline and just execute it on it. And so this is where we are currently at. So we have developed these HAL interfaces and extended it towards SPIR-V, and now we are currently in the process of extending it towards the level 0 API. And so we are especially looking into the Intel GPUs here. So we have a fully working pipeline for any ML frameworks in SPIR-V, and we are now working on the integration of the Intel NUCs or NUCs, because we see that these are really relevant within the industrial and edge applications. And level 0 for us is basically the go-to API, because we have a low driver overhead. We can directly access the devices, and that's very exciting for us. And basically, we get a free API for these new NPUs from Intel with the Gaudi 3, right? And that's very exciting for us as a small company to get ramped up so fast with our compiler technology. And basically for us, the end-to-end flow works, and the only missing piece is now to dial in the performance of the metrics units, and then we are ready to go. And so that's basically how we see this, and how we think that the UXL Foundation also is helping us tremendously with these interfaces to advance our development. Thank you for your time and for your kind attention, and I'm open for any questions in the Slack Q&A, and looking forward to meet you. You can also just reach out via LinkedIn if you want to have a more deep dive in our technology.